So in the first parts of this talk, I introduced to you the idea of building a model to predict risk. I talked a bit about verifying the model and identified a few pitfalls in prediction. In this section, I'll talk a bit more about deep learning, which is an exciting emerging field in machine learning, and go on to talk about some of the ongoing challenges with machine learning in general. Now, this figure is a bit outdated. It shows the popularity of different machine learning algorithms over time. And you can see here that starting in the end of the 80s, going through the 90s, artificial neural networks have risen in popularity and have become one of the dominant machine learning tools in the literature. So what is an artificial neural network? What is deep learning? Well, I'm going to try to build an intuition here, and by no means will this segment be exhaustive, but I find it helpful to think about a neural network, an artificial neural network, or the unit of an artificial neural network, which they call perceptron, as simply a linear regression. So we have the schematic here, which is a conceptual diagram of a neural network, but it's also a diagram of a linear regression model. And what we have here is the input X, for which there are D different features, D different predictors, and the output Y connected by a series of lines. And the lines represent the weights of the neural network model. So we can say that Y equals the linear combination of the weighted input, where the value of the input are the value of the nodes, and the value of the weights are the value of the edges of the diagram here. This is a basic linear regression, which you could generalize to a logistic regression by transforming the weighted combination so that the output is, say, binary. It's either 0 or 1. Now, all deep neural networks really are is this basic building block, which is the linear regression model, stacked on top of each other and pass through some nonlinear transformation, which we'll represent with an F here, such that the output, the very final output, is the weighted combination of some nodes we call the hidden layer. So for example, it's the one weight assigned to the hidden node 1 plus the second weight applied to a hidden node 2 and so on, run through some sort of nonlinear transformation like a hyperbolic tangent function or something complex like that, where the input values, those hidden nodes themselves, as they're called, are themselves a linear combination of the input from the layer before, weighted accordingly. And what the neural network's going to do is going to try to find the set of weights, which are the edges in the schematic, that give you the best prediction, that give you the least amount of error, or the smallest residual, or the minimal loss. And the reason these nonlinear transformations are used, as opposed to just using a linear model, is that the transformations allow it to find very complex mappings between the input and the output that aren't simply of the form like y equals mx plus b. Now, these nonlinear transformations make deep neural networks quite powerful, but another thing that makes them very powerful is that there are many architectural variants or variations in how these nodes and weights are configured that make them well suited for specific types of problems. In the diagram before, we showed what they call a fully connected layer, which is when all of the inputs are connected to all of the hidden nodes, which are connected to all of the outputs. So every node in one layer is connected to every node in the next layer, which is connected to every node in the following layer, and so on. Now, there are other types of architectural variants that accommodate different types of data input. One is convolutional neural networks, which is where the nodes on the input are connected to the nodes in the next layer if they're adjacent to each other. So we see the first two nodes from layer 1 are connected to node 1 in layer 2, and the last two nodes in layer 1 are connected to the last node in layer 2. And what this architecture is really good at is identifying spatial relationships. For example, in a DNA sequence or amino acid sequence, or where they have perhaps got most attention is in an image. And there are other architectural variants which are a little bit more complicated, but are useful for specific problems, like the recurrent neural network, which is good for time-varying signal as well as sequences, as well as graph convolutional neural networks, which work well with graphs. And in biology, that would be, say, protein-protein interaction networks or protein structures themselves. Another useful thing about neural networks is that they're a very general tool for solving lots of different problems. And you can create these different frameworks where you can have multiple inputs and multiple outputs of different types and build a single unified model that predicts the many outputs from the many inputs. So in your vanilla single task learning, you've got some input, like let's say DNA sequences, and you've got outputs that are labeled for each of the input sequences, and you want to learn a model that relates these two. In multitask learning, you've got a single input, and you've got two different types of outputs, and you're going to try to learn both of those outputs simultaneously using a single model. You could also have multimodal input, so you could have DNA and chromatin accessibility, and these are both fed into a single model to produce a single output. There's also this idea of transfer learning, which is really quite cool, where you learn a model on one task, and then you try to take that model and solve a completely different task. And then the idea here is that, you were trying to find this one robust model that can generalize to many different problems in biology. Now, here are some of the pros and cons of going and using deep neural networks. The pros are, it's a general framework for solving lots of specific problems, and it has excellent performance for structured data like image, text, and sound. And also in biology, I would add to that DNA sequences or amino acid sequences. It's also highly customizable once you know what you're doing. Now, the cons are that deep learning models have many parameters or weights, and this requires big data sets to learn. So while I said for machine learning, you should probably be thinking hundreds to thousands of samples, I'd say for deep learning, you should probably be thinking thousands, tens of thousands of samples. It also requires a lot more tinkering. It's a lot more laborious to implement these algorithms, and it can take more computer time to train them. They also can be less interpretable. Now, I put an asterisk there because there's a lot of research that goes into interpretability, and that's one of the areas that I'm very interested in. You may see this in some of my own videos. But unless you're doing something sort of left field, your model may not be clearly interpretable. And you would probably find more interpretability coming from something like a logistic regression or a decision tree, or possibly even a random forest. Finally, let me talk a little bit about some of the ongoing challenges. This is very much my opinion, looking at this field as a biologist, as someone trained in medicine, and now moving into this space of machine learning. And I'm going to break these into a few categories. The first is conceptual. And I think when applying machine learning to biological problems, we need to step back and ask ourselves, what actually is good performance? Is it just accuracy, or is the real goal to try to get better health for patients? And to think about our models at this higher level of real-world applicability. Machine learning, and by that I mean supervised machine learning, requires a gold standard to learn that function F. But what happens if none exists? And I don't think there's a really good way of solving those, other than to resort to more classical experimental approaches. Another question we should always be asking ourselves is the answer we want actually in the data we have? So we need to avoid the temptation to engage in machine learning as a kind of ritual that we have to partake in to get a publication, to have impact, and really think about it as answering a question, a research question about the data. And we need to make sure that that question is answerable with the data that we have. The final question we really need to think about is, can we accept no as an answer? And by that, I mean, if we're building a model to predict something, can we accept that it may not be predictable with the data that we have? And outside of sort of clear-cut problems like, say, cancer biology, that may indeed be the case, that the output is simply not predictable with the input that we have using the data that we have. There are also some technical challenges we need to address as well, which is how do we balance performance and interpretability? Sometimes this is a trade-off. You can get a more powerful model, a powerful deep model, but you may lose the interpretability that you get with like a simple linear regression or logistic regression. Also, how do we incorporate biological knowledge, expertise that we have in the design of the model or the design of the feature set? This is where I think biologists moving over into machine learning can really make a difference in this field by drawing on their domain expertise to engineer, as they call it, engineer new features that allow the models to perform more effectively, but also potentially be more interpretable. Also, a question of how do we deal with confounders? This is a question I get asked a lot, and I'm sorry to say I don't have a good answer yet, and hopefully in some point in the future I will. And beyond the conceptual and technical challenges, we also need to think about some of the ethical challenges as well, which is like, will our risk predictions, will our models actually improve patient quality of life? Will our models be used for adversarial reasons? Will our models learn to reinforce biases and inequities within the biomedical healthcare system? And finally, how do we ensure that AI in general, and if we're developing artificial intelligence, our AI will serve to uphold pillars of medicine like patient autonomy, beneficence, non-malevolence, justice. And this is just a plug for a paper we've put together recently called Trust in Medical AI, the challenges we face and the expertise needed to overcome them, where we talk about these big picture issues in more detail and acknowledge that moving machine learning into the biomedical field is a very hard thing to do. And not only is it hard, but the stakes are very high. Because if we make mistakes in conceptualizing machine learning or implementing machine learning or not recognizing the ethical implications of machine learning, then we can get things like useless models and uninterpretable models and models that fail to generalize, which lead to bad patient experiences and bad clinical outcomes. This can go on to cause patients to lose trust in medical AI, and that in turn could cause patients to lose trust in healthcare institutions. And so indeed, the stakes are very high. And as biomedical experts, I think we have a responsibility to engage with the machine learning literature very seriously and get involved in this conversation. Great. Thanks for your time. As always, if you have any questions, feel free to reach out. I'm always happy to talk.